If you have actual force and bending moment at the same time, the effect of actual force and the effect of bending moment will be calculated separately, and then both effects will be linearly added. Let's say you have compressive force, and the compressive force will create compressive normal stress over the cross-section of the column. And the magnitude of the compressive normal stress is P over A. And we assume the stress is uniformly distributed over the cross-section. In addition to that, the effect of bending moment will create this much bending, compressive, and tensile normal stress. On the compression side, compressive normal stress and bending normal stress will add up. On tensile side, original tensile normal stress will be reduced by compressive normal stress, so that only this small portion of tensile normal stress will remain. If your compressive force is larger, then exactly the same mechanism will apply, but on tension side, there will not be any tensile stress. But the same thing on compression side, bending normal stress and compressive normal stress will add up. So the total normal stress is compressive normal stress plus bending normal stress. Of course, compression side, the effect will add up, and tension side, it will cancel each out. So the combined effect of actual force and bending moment are obtained using linear combination. We call it principle of superposition. And you need to make sure that for principle of superposition to be valid, your material must remain in the elastic range. Here, elastic means linear relationship. We are using LRFT in reinforced concrete design in USA. In LRFT, load effect must be smaller than resistance. So that in LRFT format, safety check is done by comparing load effect against resistance. Left hand side is design bending moment if it's beam, and load effect must be smaller than resistance. My resistance is nominal bending strength of beam times phi factor. If you move right hand side to the left, then you are going to come up with this simple equation. Even though basic format of LRFT is as this, but we are going to use this simple transformed format. The reason being is because 1 is 100%. If your left hand side is, for example, 90%, then you are going to see, okay, 10% is my safety margin. If left hand side is 80%, then you have 20% of safety margin. So you can figure out that how much safety margin you have. If it's column, then design actual force must be smaller than nominal actual capacity times phi factor. Similarly, if you move right hand side to the left, then you are going to have this simple formula. So as long as the left-hand side is less than 100%, that will be okay. And at the same time, you can see that how much safety margin is there. And if your safety margin is smaller than you are using your material very effectively, so that if your ratio here is somewhere around 95% to 99, then your design is very effective. If your ratio is like 50% or 60%, then it's safe, but it is not economical design. If you have axial force and bending moment together, then your equation will be as such. You are going to add up these two to come up with just one equation. And we are going to call this type of combined equation as interaction formula. Okay, on this slide, let me go over what you have learned in the middle school days. I ask you to draw a graph of y equal minus x plus 1. Then you are going to draw x-axis and y-axis, and then your y equal minus x graph first, and then you are going to move it to this position so that you go by plus 1. Okay, so this is y equal x minus x plus 1 graph. And please note that any point on this graph, this formula, left-hand side quantity and right-hand side quantity are the same. That is the definition of equation. Alright, now, so any point on this line, left value and right-hand side, is the same. What if it's above the line, then left-hand side is greater than right-hand side. How about below? That will be left-hand side value is smaller than right-hand side value. And I'm going to move my x value to the left-hand side so that this graph is actually y plus x equal 1 graph. Similarly, above, y plus x is greater than 1 and y plus x is less than 1. Okay, and that is what we have learned in middle school days. So please pay attention that when you draw this line, below is left-hand side is smaller than 1. Okay, interaction diagram. Let's look at this as y and this as x. Then interaction diagram is like this. This is y and this is x, and my graph is this. So that this is my safer zone because interaction formula is less than 1. So less than 1 means lower part of the graph. Okay, and what this point indicate, this point P is 1 and M is 0. As you proceed from here to here, your M value increases from 0. And if you move from here to here, then your P value actual force value increase from 0 to its maximum. Okay, please note that. So that this point means column fails without bending moment. And also this point means the beam column will fail under moment with no actual force. Why? Because actual force is 0 on this line and bending moment is 0 on this line. Okay, so original interaction formula formed this line. You may wonder, what is this part then? Okay, that is the main purpose of this slide. This part again is compression failure, and this point represents bending failure. And we know bending failure is tension controlled. Tensile stress in the steel will exceed F sub y. Okay, so let's start from here. And again, from here as I go up, my compressive force and resulting compressive stress in the member will increase. At this point, my column will fail, or to be exact, my beam column will fail in tension as I go up. This compressive force and resulting compressive stress will help the steel reduce its stress. So that, please note that as you go up, as you understand, please start from this point. It's easier to understand. As I go up, compressive stress reduce or help reduce tensile bending stress so that it does not go that way, it will go that way, increasing its bending capacity. And this point is very significant. We learned about balanced condition. This theoretical condition is represented by this corner. At this corner, concrete will crush and steel will yield at the same time, and we call it balanced condition. This is a general shape of ACI interaction diagram. We are going to use ACI interaction diagram very, very intensively. Okay, when you have this type of general shape, please pay attention to this and this point first. Again, this is compression failure, or you may call it column action. And again, along this line, there is no bending moment or bending moment effect. And along this line, there is no actual force or there is no actual stress effect. Okay, this is column action, compressive failure, and this is beam action or tension control, tensile stress failure or yielding will occur in steel. And again, this was balanced condition. And you may wonder why we have this cut. If you recall, there is a minimum amount of bending stress, even though your column is perfectly straight, and even though your load is 100% concentric, we are going to assume that there is a minimal amount of bending moment due to accidental eccentricity, so that you will never reach this point because that is bending moment 0. So you are not going to reach that point. So that we are going to cut down this much. Okay, that is due to accidental eccentricity moment. And this slide is a summary of what I have explained. Once again, this point represents compression controlled, and this point represents bending failure or tension controlled. If it's tension controlled, your P factor is 0.9. If it's compression controlled, your P factor is 0.65. If it's tight column. So as you moved from here to here, your P factor will change from 0.65 to 0.9. So that in this region for tension control, there must be some break there. Okay, memorize this. Why we have this break? Because my P factor changes from 0.65 to 0.9. And second, what does this radial line mean? If you draw a straight line from origin to a certain specific spot on the interaction diagram, that means the slope, which is P over M, is constant, which means your E value is constant. For a certain E value, you can draw a straight line. That is not conceptually important, but that is very, very practically important when we design column.